So now we're going to start talking actually about neural networks finally. Let's look at our standard diagram. So our standard diagram of gradient descent, where we have a function, y with the function generates y hat, y and y hat go into the loss goes in the optimizer, optimizer goes back up to update theta based on the gradient of the loss. What we're going to be working on mostly from here on out is in here, this function. So we're now no longer going to be using polynomials. We're going to be looking and seeing what a neural network actually is. There are some cases where we will look at the loss a little bit, but for example, the optimizers, we're not going to need to go back and revisit. So all the optimizers we've seen, Atom and AdaGrad and RMS prop and using look ahead and all those still work in the context of a neural network as our function, as our model, rather than just a polynomial. Let's look at a simple function of two variables. So we have f of x1, x2 equals a0 plus a1, x1 plus a2, x2. And let's go ahead and rewrite that using matrix multiplication. Okay, so we're going to go ahead and let x equal the 1 by 2 containing x1, x2. So when we say f of x, we're going to go ahead and multiply x by a w. What do we need to multiply x by in order to get terms from here? So we'll go ahead and define w equals a1, a2. And so, of course, when we multiply x by w, this is going to be x1a1 x1a1 plus x2a2. So that'll give us these two terms. So we're going to go ahead and add plus a b, where b is going to be defined to be just a matrix with a single entry in it, which is going to be a0. So if we multiply this out, right, this is x1, x2 times a1, a2 plus a0. And that equals which equals a 1 by 1 matrix. So we have incoming a 1 by 2 matrix and outgoing a 1 by 1 matrix. So we can extract our answer from there. We can also use this matrix approach if we want to have more than one output. So let's look at some outputs. So let's look at, let's say, we want to have f1 of x, which equals, let's say, some z1, and that equals something like this. Okay, so we've got two outputs. Not uncommon, right? If when we're doing neural networks, we might often at the end be generating more than one output. If we're doing multi-class or multi-label classification, for example, we might be regressing to, let's say we're estimating a point on a picture. So where someone's nose is, that naturally would be represented as the xy coordinates on the image. So that would be two numbers that were coming out. If we're looking at chess, we may have a whole bunch of different outputs predicting the probabilities of where we should be moving. So we can still represent this as a single matrix multiplication with an addition. So what I'm looking at doing is let's look, and again, we'll represent x equals x1, x2. But now what we're going to get out as an output, right? We got as an output here a 1 by 1. Our input, again, was a 1 by 2. This is a 2 by 1. This is a 1 by 1. What we're going to want instead is our output to be a 1 by 2 with the two values. So our goal is that we are going to end up with these two values, A0 and okay. So let's work our way to get there. Our x is going to look like this. We're still going to go ahead and look at f of x. But we're going to say f of x is now a vector, right? A 1 by 2 vector. So that's what we're going to get here. We're going to represent this as xw plus v. But w is now going to be, so x is going to be 1 by 2. And w is going to have to be different, right? W, what we would have said before, is it's a1, a2. But now we're going to add a separate column with a4, a5. And b is also going to have to be a different size. So here we've got a 2 by 2. And this is now going to have to be a 1 by 2 with a0 and a3. So let's just go through the calculations again to make sure we agree. So this is going to equal x1, x2 times a1, a2, a4, a5 plus a0, a3. And that's going to equal, the first column is going to be x1, a1 plus x2, a2. And then the second column is going to be x1, a4 plus x2, a5. And then we'll add in a0, a3. And if we look, we do end up with the correct results as we add these two matrices. So we don't need to know a lot about linear algebra for neural networks. Basically what we need to know how to do is multiply matrices and add matrices, and that's it. So we can now look at the fact that we can deal with functions that take multiple inputs, okay? And the number of inputs is going to be the number of rows of W. And we can also produce multiple outputs. And that number of outputs is going to be the number of columns of both W and B. So if we just define a W and B, that'll tell us what the input shape needs to look like and what the output shape needs to look like. And we can string these together. So let's say we have f of x of this form. If x is equal to a 1 by n array, then what do we know about W? Well, W is going to equal n times, and then we get to decide how many outputs do we want for this. Okay, so we'll go ahead and let's let S be our, what we're going to call the size. So this is going to be an n by S, and B is going to equal a 1 by S. And so that means f of x is going to equal a 1 by S. And when I say equal here, I mean that the dimensions are going to be a 1 by S. So those are going to be of those sizes. What we do in neural networks is we make various layers. So we have coming in an x that is a 1 by n. So we have however many inputs we have. And then this goes through a matrix of n by some size, let's call it S1. So we have S1 outputs here. So this is a 1 by S1. And then we can choose a different weight matrix here. So let's call this layer 1, and this layer 2, and this all the way to layer L for the number of layers. I'll use a cursive L there. So we can have, from layer to layer, different numbers of outputs. We can take these in outputs and we can shrink them down to 1, or we could go up to 100 or 1,000 or something like that. So this now serves as the input to the next layer. And then we have an output here. So this one might be W2, might be of size S1 by S2, all the way till finally our WL is of size SL minus 1 times SL. So what comes out is a 1 by SL array, and this is the final output. So we've got all these layers. And for each layer, we define a size. Now, of course, I'm just leaving out the fact that we also have our B's. Our B's, we have a B1 also, and a B2 all the way to a BL, and I'll just show them. So B1 is 1 by S1, B2 is 1 by S2, and BL is 1 by SL. So we have all these matrix multiplications, and we just compose them together and get an output. Except that's not the whole story. And the reason for that is a problem we have. And the problem we have is that something of the form f of x equal xw plus b for matrices is closed under composition. What do I mean by that? Well, let's say we have f of x is xw plus b, and g of x, so let's go ahead and call it w1 and b1, and g of x is xw2 plus b2. So these could be, for instance, the first two layers here. This is f, this is g. The question is, what happens if we look at f of g of x? So what I'm saying is that this is closed under composition. What I mean is when we compose like this, that we're going to end up with something that we can rewrite as a single x times a single matrix plus a single matrix. But let's just go ahead and multiply this out. So f of g of x is going to be equal to, well, let's see, this is f of xw2 plus b2, and this equals, so f of this equals, so this is our new x, so this is xw2 plus b2, right, in here, times w1 plus b1. Looks okay so far. Let's just multiply this out. So this equals x w2 w1 plus b2 w1 plus b1. And let's just throw in here some sizes, okay, just to make sure. This is kind of just a double check to make sure that this is all working right. So let's say w1 is equal to 2 by 2, b1 then would equal a 1 by 2, and that w2 is equal, well, let's just see what that has to be. Since we're taking g of x and then applying f of x, that means the input to f is the output of g. So the output of g had better be a 1 by 2. So that means that b2 is a 1 by 2. And let's just go ahead and make so that this one is different. We'll make this a 1 by 3 and a 2 by 3. And let's make w2 be, how many inputs do we have? Let's say there's one input to g. So it's going to be a 1 by. So let's just look at these sizes then. b1 is a 1 by 3. b2 is a 1 by 2 multiplied by a 2 by 3. So that's going to correctly give us a 1 by 3. And we also know that it's an output of f, and so f should have a result of a vector of size 3. And now we can look at xw2, w1. The order in which we've been doing the multiplications is x times w2, and then that times w1. However, we know that matrix multiplication is associative. That means if we have three matrices A, B, and C that we multiply together, we can either multiply together B times C first, and then multiply the result of that by A, or we can multiply A and B first, and then multiply the result of that by C. So that says we can choose to multiply x times w2, and then that times w1, which is our original here, x times w2 and then times w1, or we can choose to multiply in this direction. So we know w2 is a 1 by 2, and multiplying that by w1, which is a 2 by 3, so that all fits, which ends up with a 1 by 3. So we can actually just do this multiplication and end up with x times a new matrix, the result of multiplying w2 by w1, let's call that w prime, and we can add that to the result of doing this multiplication and adding it to this vector and getting some new b prime. So what's happened? Well, we took two of our functions of this form and we applied them together, and we found that that could be replaced with another function by that form with different w and different b. What that really says is this entire set of L layers could be replaced by a single layer as long as we chose a w that was a n by s sub l size and b a 1 by sl size, and we had to choose these appropriately, the w and the b. So we don't get any more power by adding more layers. That's a problem. Okay. And the problem is we have it's all linear. We're doing linear here, and then we go into linear here, and we go all the way to linear here, which means we end up with linear. So all we're left with is, after all this composition, all this depth, is simple linear multiplication. We don't get any more power. So we need to add some nonlinearity, and that's what we're going to do. So this is not the entire picture. This is close to the entire picture.